The sun is not a solid object. It has no crust, no skin, no sealed surface the way Earth does. It is an enormous sphere of superheated plasma, a churning, magnetic, electrically charged ocean of gas so massive that 1,300,000 Earths could fit inside it. And yet, even something that large, that ancient, that powerful, opens up. A hole appeared on the surface of the sun. Not a metaphorical hole, not a crack in rock or a gap in ice, a coronal hole, a region where the sun's magnetic field lines, instead of looping back into the solar surface the way they normally do, simply stretch outward into space and never return. Open, exposed, releasing. And through that opening, a river of charged particles, electrons, protons, helium nuclei, is flowing outward at speeds between 300 and 800 kilometers per second. That stream has a name, the solar wind. And one specific burst of it, accelerated and amplified by the geometry of the hole itself, is aimed directly at Earth. This is not a prediction. This is not a model. This is something that solar observatories have already detected, measured, and tracked in real time. The question that matters, the one that has occupied physicists, space weather forecasters, and satellite engineers for decades, is not whether it will arrive. It will. The question is what it will do when it gets here. To understand that, you have to understand the sun. Not as a symbol, not as the warm light coming through a window in the morning, but as the object it actually is. A nuclear furnace 4.6 billion years old, sitting 93 million miles from where you are right now, and still, after all that time, undergoing processes that science is still working to fully explain. The sun contains 99.8% of all the mass in our entire solar system. Every planet, every moon, every asteroid, every comet, every grain of dust drifting between the orbits of Mars and Jupiter, all of it together makes up less than 0.5% of what the solar system contains. The sun is not a part of the solar system. The solar system is, in every meaningful physical sense, an extension of the sun. At its core, the temperature reaches 15 million degrees Celsius, not on the surface, in the core. That heat comes from nuclear fusion, hydrogen nuclei colliding with such force that they merge, forming helium and releasing energy in the process. Every second, the sun converts approximately 600 million metric tons of hydrogen into helium. In that conversion, about 4 million metric tons of mass are turned directly into energy, following the relationship that Einstein described in 1905. Energy equals mass times the speed of light squared. The speed of light is approximately 300,000 kilometers per second. Square that. Multiply it by 4 million metric tons. The number that comes out is the reason the sun has been shining for 4.5 billion years and will continue shining for approximately another 5 billion. That energy travels outward from the core, but it does not travel quickly. In fact, a photon of light generated in the solar core takes somewhere between 10,000 and 100,000 years to work its way through the radiative zone, the thick inner layer of the sun, before it even reaches the outer convective layer. 10,000 years. The light that left the core of the sun during the last ice age on Earth is still making its way toward the surface. Once it finally escapes into space, it covers the 93 million miles to Earth in approximately 8 minutes and 20 seconds. That contrast alone, 100,000 years inside the sun, 8 minutes across interplanetary space, tells you something important about the density and complexity of what we are dealing with. The surface of the sun, called the photosphere, sits at a temperature of approximately 5,500 degrees Celsius. That is the bright disk you see in the sky. But above the photosphere, something strange happens. The temperature rises again, dramatically. The chromosphere, the thin layer just above the photosphere, reaches tens of thousands of degrees. And then the outermost layer, the corona, the ghostly halo of plasma visible during total solar eclipses, reaches temperatures between 1 million and 3 million degrees Celsius. This makes no immediate physical sense. If you walk away from a campfire, you get colder, not hotter. Energy dissipates with distance, and yet the sun's atmosphere gets dramatically hotter the further you move from its surface. This is called the coronal heating problem, and it remains one of the great unsolved questions in solar physics. Several mechanisms have been proposed: Alphen wave dissipation, nanoflare heating, magnetic reconnection events, and the current scientific consensus points to magnetic processes as the primary driver. But the precise mechanism, the full chain of cause and effect, is still being studied by missions like NASA's Parker Solar Probe, which has flown closer to the Sun than any human-made object in history, passing through the outer corona itself. The corona is also where the solar wind originates. And the solar wind is not a gentle breeze. It is a continuous supersonic outflow of plasma, ionized gas, expanding in all directions from the Sun at speeds that, at Earth's distance, average around 400 kilometers per second. That is 1.4 million kilometers per hour. To put that in terms a human brain can process, if you could travel at that speed, you would circle the entire Earth at the equator in approximately 100 seconds. You would travel from New York to Los Angeles in roughly 19 seconds. The solar wind fills the entire solar system. It shapes the magnetospheres of every planet that has one. It sculpts the tails of comets, always pointing away from the Sun regardless of the direction the comet is moving, because the solar wind pushes the ionized gas tail directly outward. It creates the heliosphere, the enormous magnetic bubble, stretching well beyond the orbit of Pluto, that separates our solar system from interstellar space. But the solar wind is not uniform. It does not flow at the same speed or density in all directions. Its structure is determined by the Sun's magnetic field, one of the most complex and dynamic magnetic structures in the known solar system. The Sun's magnetic field is generated by the movement of electrically charged plasma inside the Sun itself. As that plasma moves, rising, falling, rotating at different speeds at different latitudes in a process called differential rotation, since the equator rotates faster than the poles, it drags and twists the magnetic field lines with it. Over time, those field lines become tangled, stressed, and concentrated into powerful bundles. Where those bundles pierce the photosphere, they suppress the normal convective flow of hot plasma rising from below. The surface cools slightly in those regions, from 5,500 degrees to around 3,500 degrees. They appear dark against the surrounding photosphere. They are sunspots. Sunspots are not small features. A large sunspot group can span a region larger than the entire diameter of Earth. And they are indicators of intense magnetic activity, regions where the stored magnetic energy is highest, and where the most dramatic solar events, including solar flares and coronal mass ejections, are most likely to originate. Coronal holes are different from sunspots, but they are equally a product of the Sun's magnetic architecture. Where sunspot regions involve closed, highly tangled magnetic loops, coronal holes involve open magnetic field lines, lines that extend outward from the Sun's surface and connect to the broader heliospheric magnetic field without looping back. Because the field is open, the hot plasma of the corona can stream freely outward along those lines, rather than being trapped and confined. The result is a fast solar wind stream, accelerated and relatively unimpeded, flowing outward into interplanetary space. From Earth, coronal holes appear as dark patches on the solar disk when observed in extreme ultraviolet or X-ray wavelengths, wavelengths that reveal the corona's structure. They can persist for weeks or months, rotating with the Sun. As the Sun completes one full rotation roughly every 27 days as seen from Earth, a coronal hole that faces our planet will do so again approximately one rotation later. This makes them somewhat predictable, unlike the sudden explosive events of solar flares or coronal mass ejections. The hole that opened recently is large enough that the solar wind stream it is generating is measurably faster and denser than the ambient solar wind, large enough that space weather monitoring agencies flagged it in advance, and the geometry of its position on the solar disk placed it in a direct line with Earth's orbital position. The stream is already in transit, moving at speeds between 500 and 800 kilometers per second, the distance from the Sun to Earth. One astronomical unit, approximately 150 million kilometers, becomes a journey of roughly 2 to 4 days. It is already on its way. The physics of what happens when it arrives, what Earth's magnetic field will do, what the charged particles will interact with, what the atmosphere will produce in response, is where this story becomes far more complex and far more consequential than most people realize. Because the story of a hole in the sun is not really about the sun. It is about what happens here. Space weather is a field that barely existed as a formal scientific discipline 50 years ago. Today, it has its own forecasting centers, its own satellites, its own international alert systems, and its own scale of measurement, because humanity learned, through a series of increasingly costly lessons, that the sun does not simply shine. It erupts, it exhales, it throws. And what it throws travels across 150 million kilometers of interplanetary space and collides with a planet that has built its entire technological civilization on systems that are exquisitely sensitive to exactly what the sun is capable of producing. The coronal hole driving the current event is not a minor feature. Observations from NASA's Solar Dynamics Observatory, a spacecraft that has monitored the sun continuously since February of 2010, capturing an image of the full solar disk every 12 seconds in 10 different wavelengths of light, show a structure that spans a significant fraction of the sun's visible hemisphere. In extreme ultraviolet imagery, it appears as a dark, irregular region where the corona is simply absent. Cooler, emptier, open. The contrast with the surrounding active regions, bright, tangled, magnetically dense, makes it unmistakable. The Solar Dynamics Observatory orbits Earth at an altitude of approximately 36,000 kilometers in a geosynchronous orbit that keeps it in constant communication with ground stations. It transmits roughly 1.5 terabytes of data every single day. That continuous stream of solar imagery is what allows space weather forecasters at NOAA's Space Weather Prediction Center in Boulder, Colorado, and at equivalent agencies in Europe and Japan to identify features like this coronal hole days before their associated solar wind streams reach Earth. The warning time is real. The data is real. And what the data shows is a fast solar wind stream, denser than the ambient background wind, moving at speeds that forecasters estimated between 500 and 700 kilometers per second, that left the sun's corona and entered interplanetary space on a trajectory aligned with Earth's position. Why does an open magnetic field accelerate the solar wind? Under normal conditions, the solar wind emerges from the corona at a range of speeds. The slow solar wind, originating near the magnetic equator and from the boundaries of closed magnetic field regions, travels at roughly 300 to 400 kilometers per second by the time it reaches Earth. The fast solar wind, streaming from coronal holes where the field is open and unobstructed, regularly reaches 500 to 800 kilometers per second. The difference is not arbitrary. In open field regions, the plasma has a direct, unimpeded path along magnetic field lines that extend all the way into the heliosphere. There is no magnetic cage holding it back. The plasma, electrons, protons, alpha particles, accelerates along those open lines and escapes. The coronal hole acts in physical terms as a nozzle. The geometry of the open field collimates and accelerates the outflow. This is where the concept of solar wind pressure becomes critical. The force that a solar wind stream exerts on a planetary magnetosphere is not simply a function of its speed, it is a function of its dynamic pressure, which depends on both the density of the particle stream and the square of its velocity. Double the speed, and you quadruple the dynamic pressure. A fast stream from a large coronal hole can carry dynamic pressures several times higher than the ambient solar wind. When that pressure increase arrives at Earth, it compresses the magnetosphere, the magnetic bubble generated by Earth's internal dynamo, inward on the sunward side, sometimes dramatically. Under quiet solar wind conditions, the boundary of Earth's magnetosphere on the sunward side, called the magnetopause, sits at roughly 10 Earth radii from the planet's center. 10 Earth radii is approximately 64,000 kilometers. That is the distance at which the solar wind's dynamic pressure and Earth's magnetic pressure reach equilibrium. When a fast, dense solar wind stream arrives and that dynamic pressure spikes, the magnetopause can be pushed inward to 8, 7, even 6 Earth radii. In extreme historical events, it has been pushed to within 2 or 3 Earth radii, which means inside the orbits of geosynchronous satellites, those same spacecraft that provide global communications, weather monitoring, and navigation. The precise consequences of what is coming depend on one factor above all others: the orientation of the interplanetary magnetic field embedded in the solar wind stream. The solar wind does not arrive as bare particles. It carries a magnetic field with it, the heliospheric magnetic field, which is an extension of the sun's own magnetic field, dragged outward by the expanding plasma. As this field travels through interplanetary space, it retains a component directed either northward or southward relative to Earth's magnetic equator. That component is called the BZ component of the interplanetary magnetic field, measured in units of nanotesla. When BZ points northward, in the same direction as Earth's magnetic field on the sunward side, the interplanetary magnetic field and Earth's field are aligned. They resist merging. The magnetosphere remains relatively closed. Charged particles from the solar wind have difficulty penetrating deep into the magnetospheric system. The geomagnetic response is muted. When BZ points southward, opposite to Earth's field, something entirely different happens. The two magnetic fields merge at the magnetopause through a process called magnetic reconnection. Field lines from the sun's magnetic field link up with field lines from Earth's magnetic field, creating open channels through which solar wind plasma can flow directly into the magnetosphere. Energy stored in the magnetic field is explosively released. Plasma is accelerated. Currents flow through the magnetospheric system and down into the ionosphere. The aurora appears. This is the fundamental variable that every space weather forecaster is watching. The speed of the incoming stream, its density, its dynamic pressure, all of that can be estimated days in advance from solar observations. But the BZ component cannot be reliably predicted until the solar wind stream is measured by a spacecraft sitting at a specific point in space called the first Lagrange point, L1, approximately 1.5 million kilometers sunward from Earth. At that distance, a solar wind stream traveling at 600 kilometers per second gives forecasters roughly 45 minutes of warning before it reaches Earth. 45 minutes. That is the actual lead time for the most critical piece of information in space weather forecasting. The spacecraft responsible for that measurement is called the Deep Space Climate Observatory, or DSCOVR, operated jointly by NOAA, NASA, and the United States Air Force. It was launched in February of 2015 and placed in a halo orbit around the L1 point. Its primary instrument for solar wind monitoring, the Faraday cup and the magnetometer, measures the solar wind's speed, density, temperature, and magnetic field orientation in real time, transmitting that data to ground stations where it feeds directly into operational space weather forecasting models. DSCOVR did not arrive at L1 without context. Its predecessor, a NASA spacecraft called ACE, the Advanced Composition Explorer, had occupied roughly the same position since 1997. Between AC and DSCOVR, humanity has had continuous in-situ solar wind measurements at L1 for nearly 3 decades. That data archive is one of the most scientifically valuable datasets in all of heliophysics. What that archive shows is a history of geomagnetic storms, events in which the solar wind's interaction with Earth's magnetosphere produces measurable, sometimes severe disturbances in the geomagnetic field. Those storms are classified on a scale from G1 to G5, where G1 represents minor disturbances and G5 represents extreme events capable of causing widespread damage to power infrastructure, communication systems, and satellite operations. The current incoming stream has been forecast to produce conditions at the G2 to G3 range, moderate to strong, with the possibility of escalation if the BZ component turns strongly southward upon arrival. Most people know nothing about this scale. Most people have never heard of a geomagnetic storm index. And that gap between what the sun is capable of doing and what the general public understands is not a trivial matter, because the infrastructure of modern civilization sits directly in the path of what the sun periodically sends our way. Power grids, undersea fiber optic cables, GPS constellations, radio communications, pipeline monitoring systems. All of them interact in different ways with the geomagnetic environment that the sun controls. The history of what happens when that environment is disturbed is far more dramatic and far more recent than most people imagine. On the 13th of March, 1989, a geomagnetic storm classified at the G5 level swept across North America. The entire province of Quebec lost electrical power in approximately 90 seconds. 6 million people sat in the dark for up to 9 hours. Transformers failed as far south as New Jersey. The storm induced electrical currents in the ground, called geomagnetically induced currents, that overwhelmed the protective systems of high-voltage transformers faster than any operator could respond. The aurora that night was visible from Texas and Florida, and 1989 was not the largest event on record. That distinction belongs to an event that occurred in September of 1859, more than a century and a half ago, before the electrical grid, before satellites, before any of the infrastructure that modern civilization depends on. It is called the Carrington event, named for the British astronomer Richard Carrington, who observed the solar flare that preceded it. The geomagnetic storm that followed was so intense that the only technology of the era vulnerable to it, the telegraph network, failed catastrophically across North America and Europe. Telegraph operators reported receiving electrical shocks from their equipment. Some telegraph stations caught fire. The aurora was visible near the equator, from Cuba, from Hawaii, from Colombia. If an event of equivalent magnitude struck today, the estimated economic damage ranges from $1 trillion to $10 trillion. Recovery time for the most severely affected power grid infrastructure, specifically the large high-voltage transformers that are custom manufactured and take 1 to 3 years to replace, could extend to years, not weeks. That is the scale of what a coronal hole and its associated solar wind stream represent at their most extreme. The event currently in progress is not a Carrington-scale event. The data does not suggest that. But it belongs to the same physical family, the same chain of cause and effect that begins with the sun's magnetic architecture, flows through 150 million kilometers of space, and terminates at the boundary of Earth's own magnetic shield. Understanding what that shield is, how it works, and precisely where it is most vulnerable, that is what the physics of the next hours will reveal. Earth is not defenseless. 4.5 billion years of planetary evolution produced a magnetic shield of extraordinary complexity. A structure generated not at the surface, not in the atmosphere, but deep inside the planet itself, in the outer core, where liquid iron alloy circulates in convective currents driven by the heat, escaping from the solid inner core below. That moving, electrically conducting fluid generates electrical currents, and those currents generate a magnetic field. The process is called the geodynamo. It has been operating with interruptions and reversals for at least 3.5 billion years. Without it, Earth's surface would be exposed to the full flux of the solar wind, and the atmosphere, particularly the water vapor and lighter gases in the upper layers, would be gradually stripped away, particle by particle, over geological time. Mars is the most immediate example of what happens to a planet that loses its geodynamo. Mars once had a magnetic field, liquid water on its surface, and a substantially thicker atmosphere. The dynamo died, probably around 4 billion years ago. The solar wind went to work. Today, the Martian atmosphere is less than 1% as dense as Earth's, composed almost entirely of carbon dioxide, and the surface is a frozen, irradiated desert. Earth avoided that fate because its core kept moving. The geomagnetic field that results from the geodynamo is roughly dipolar. It resembles, in its large-scale structure, the field of a bar magnet, with field lines emerging from one magnetic pole, arcing through space and re-entering at the other. The magnetic North Pole and the geographic North Pole are not the same point. Currently, the magnetic North Pole sits in the Canadian Arctic, and it has been drifting toward Siberia at a rate that has accelerated in recent decades, moving at approximately 55 kilometers per year as of the most recent measurements. The field is not static. It breathes. It shifts. It has reversed its polarity hundreds of times over Earth's history, the last reversal occurring approximately 780,000 years ago during an event called the Brunhes-Matuyama reversal. The field's strength is also not uniform across the planet's surface. There is a region over the South Atlantic, stretching roughly from South America to southern Africa, where the field is measurably weaker than anywhere else on Earth. This region is called the South Atlantic anomaly. At its center, the field intensity is roughly 30% weaker than the global average. Satellites passing through this region experience elevated rates of single-event upsets, computational errors caused by energetic particles penetrating the spacecraft's electronics, because the magnetic shielding overhead is thinner there. The International Space Station, whose orbit passes through the South Atlantic anomaly on every circuit, has additional shielding in crew quarters specifically to reduce radiation exposure during those transits. The anomaly is not a threat to life on the surface. The atmosphere provides its own shielding, but it is a precise, measurable demonstration of the geomagnetic field's variability and of the real-world engineering consequences of that variability. The field's structure in space is far more complex than a simple dipole. The solar wind deforms it continuously. On the sunward side, the solar wind's dynamic pressure compresses the field into a blunt, rounded shape. On the night side, the field is stretched into an enormously elongated structure called the magnetotail, extending hundreds of Earth radii downwind, sometimes as far as 1,000 Earth radii, or approximately 6.4 million kilometers. The magnetotail is where significant amounts of solar wind plasma that has entered the magnetospheric system accumulate and are energized. Upstream of the magnetosphere, before the solar wind even reaches the magnetopause, it encounters a shock wave. The solar wind travels faster than the speed at which magnetic disturbances propagate through plasma, faster than the Alfvén speed and the magnetosonic speed. When a supersonic flow encounters an obstacle, it forms a shock. Earth's shock is called the bow shock, and it sits at roughly 14 Earth radii on the sunward side, further out than the magnetopause itself. As the solar wind crosses the bow shock, it slows abruptly, heats dramatically, and becomes turbulent. The region between the bow shock and the magnetopause is called the magnetosheath, a churning, disordered zone of shocked solar wind plasma. The plasma does not simply slide around the magnetopause cleanly. It interacts with it, probes it, and at locations where the interplanetary magnetic field is oriented to allow reconnection, it penetrates it. Magnetic reconnection is not a peripheral detail. It is the central mechanism by which energy from the solar wind enters the magnetospheric system. The physics of reconnection was first described mathematically by James Dungy of Imperial College London in 1961. Dungy proposed that when the interplanetary magnetic field carried by the solar wind has a southward component, anti-parallel to Earth's northward-facing field on the dayside magnetopause, the two fields can merge at the magnetopause boundary. The merged field lines, now connected between the solar wind and Earth's magnetosphere, are then carried tailward by the solar wind flow, forming a long-stretched configuration in the magnetotail. Eventually, those stretched field lines reconnect again in the tail, releasing stored magnetic energy explosively and accelerating plasma both tailward into the solar wind and earthward toward the planet. The earthward-directed plasma and energetic particles follow the reconnected field lines down into the polar regions, into the auroral zones, and deposit their energy in the ionosphere. Light is produced. The aurora. Dungy's model, now called the Dungy cycle, has been confirmed by decades of in situ spacecraft measurements. The entire sequence, from dayside reconnection at the magnetopause to nightside reconnection in the tail, and the subsequent earthward injection of plasma, takes roughly 1 to 3 hours. During geomagnetic storms, when the southward BZ component of the solar wind is sustained over many hours, the Dungy cycle runs continuously and intensifies, driving the ring current. The ring current is a feature of Earth's magnetosphere that most people have never heard of, yet it is the primary driver of the global geomagnetic disturbance measured during storms. It is a toroidal, donut-shaped, electrical current flowing westward around Earth, carried by energetic ions trapped in the magnetic field at altitudes between roughly 2 and 7 Earth radii above the equator. These ions, primarily oxygen ions from Earth's own ionosphere, along with protons from the solar wind, are injected into the inner magnetosphere during geomagnetically active periods and drift around the planet under the influence of the magnetic field's gradient and curvature. A westward drifting positive charge constitutes a westward current, which by Ampere's law generates a magnetic field opposing Earth's main field. The result is a measurable decrease in the magnetic field strength recorded by magnetometers at Earth's surface, a decrease that defines the geomagnetic storm itself. The magnitude of that decrease is measured by an index called DST, the Disturbance Storm Time Index, calculated from magnetometer readings at 4 low-latitude stations distributed around the globe: Hermanus in South Africa, Kakioka in Japan, Honolulu in Hawaii, and San Juan in Puerto Rico. Each station measures the horizontal component of the local magnetic field continuously. When the ring current intensifies and the global field drops, all 4 stations record the decrease in synchrony, and the average becomes the DST index, expressed in nanotesla. A DST of -30 to -50 nanotesla indicates a moderate storm. -100 nanotesla is a severe storm. During the March 1989 event, DST reached approximately -589 nanotesla. During the Carrington event of 1859, estimates derived from historical magnetometer records from Colaba Observatory in Bombay, one of the few functioning instruments at the time, suggest the DST may have reached -1,600 to -1,700 nanotesla, a number so far outside modern experience that it represents a different order of magnitude entirely. The ionosphere, the uppermost electrically conducting layer of Earth's atmosphere, sitting between roughly 60 and 1,000 kilometers altitude, is where the energy deposited by the storm system becomes tangible at the surface level. During geomagnetic storms, the ionosphere heats and expands. Its electron density becomes irregular and turbulent. Radio waves traveling through it, including the high-frequency radio bands used for long-distance communications and aviation, are absorbed, reflected unpredictably, or scattered. GPS signals, which travel from satellites at 20,000 kilometers altitude through the ionosphere to receivers on the ground, are delayed by the ionosphere's electron content in ways that vary with space weather conditions. Under quiet conditions, ionospheric GPS errors are well characterized and correctable. During major storms, the corrections fail. Positioning errors that normally sit at less than 1 meter can exceed tens of meters. For aviation approaches, for precision agriculture, for autonomous vehicle navigation, for offshore drilling platforms, the difference matters. At lower altitudes in the thermosphere, the heating is direct and measurable. The thermosphere expands upward during geomagnetic storms as energy is deposited from above. The density at a given altitude increases. For satellites in low Earth orbit, at altitudes between 200 and 1,000 kilometers, this increased atmospheric density produces greater aerodynamic drag. Orbital decay accelerates. Satellites lose altitude faster than their operators plan for. In February of 2022, SpaceX launched 49 Starlink satellites into a low deployment orbit of approximately 210 kilometers, intending to raise them to their operational altitude afterward. A geomagnetic storm struck the day after launch. The increased thermospheric density generated drag forces up to 50% higher than predicted. 40 of the 49 satellites, 82% of the batch, re-entered the atmosphere and were destroyed. The financial loss was estimated at approximately $50 million from a single moderate storm event. That event was classified at the G1 level, the lowest category on the scale. What is approaching now sits in a different bracket. And the physics of what happens when a sustained, fast, magnetically southward solar wind stream presses against the magnetosphere for 6, 12, or 18 consecutive hours, running the Dungy cycle without interruption, injecting plasma continuously into the ring current, driving DST steadily negative, is not theoretical. It has happened before. The instruments recorded it. The infrastructure felt it. The only question the data cannot yet answer is how far south the BZ will turn and for how long it will hold. Everything else follows from that single number. On the 1st of September, 1859, Richard Carrington was doing what he did most clear mornings, projecting the sun's image through his telescope onto a white card in his private observatory in Red Hill, Surrey, and carefully tracing the positions and shapes of the sunspot groups visible on the solar disk. Carrington was not a professional astronomer in the institutional sense. He was a wealthy brewer's son who had built his own observatory and dedicated himself, with extraordinary methodical discipline, to the systematic observation of sunspots. He had been doing this for years, compiling one of the most detailed records of solar surface activity in existence at the time. At 11:18 in the morning, he saw something no astronomer had ever documented before. Within the complex of sunspots he was sketching, 2 intensely brilliant white patches of light appeared, so bright they nearly overwhelmed the projected image. They moved, they changed shape. Within 5 minutes, they had faded and disappeared. Carrington sketched their positions immediately, then ran to find a witness. By the time he returned with another observer named Richard Hodgson, who had independently seen the same event from his own observatory, the light had already gone. The two men had observed the first recorded solar flare in history. What Carrington saw was the optical signature of an enormous release of magnetic energy in the solar atmosphere, the sudden conversion of stored magnetic energy into heat, particle acceleration, and radiation across the electromagnetic spectrum. The white light visible to Carrington was produced by an intense heating of the photosphere itself, heated so rapidly and so powerfully by energy cascading down from the flare site that it briefly outshone the surrounding solar surface. White light flares, as they are now called, are among the most energetic class of solar flare events and are still relatively rare, a testament to just how extreme the September 1859 event was. 17 hours later, the geomagnetic storm began. The speed at which the associated coronal mass ejection, the enormous cloud of magnetized plasma launched by the flare, traveled from the Sun to Earth implies a transit velocity of approximately 2,300 kilometers per second. The typical transit time for a coronal mass ejection is 2 to 4 days. The Carrington CME covered the same distance in approximately 17.5 hours. That speed is so far beyond the normal range that for decades, historians of science debated whether the timing was correct. It was. The event remains the fastest confirmed solar ejecta transit in the observational record, a consequence of the extreme energy of the eruption and the fact that the preceding solar activity had already cleared and preconditioned the interplanetary medium ahead of it, a phenomenon now called the cleared path effect, in which earlier CMEs sweep the interplanetary space of denser ambient solar wind, allowing subsequent ejecta to travel with less resistance. The telegraph operators of North America and Europe experienced the storm directly. Machines sparked, wires caught fire. Some operators, after disconnecting their batteries entirely, found that the geomagnetically induced currents flowing through the telegraph lines were sufficient to operate the Morse code machines on their own, using the Earth itself as the power source. The aurora that night was visible at latitudes where it had never been recorded. Equatorial observers in Colombia, Cuba, Hawaii, and Queensland in Australia reported vivid displays of red and green light filling the entire sky. The Carrington event established in a single catastrophic demonstration a fact that science would spend the next 160 years trying to fully quantify. The Sun and the Earth are not separate, independent systems. They are coupled. The Sun's behavior directly, physically, and measurably affects conditions on and around Earth, and the intensity of that coupling scales with the magnitude of the solar event. The 20th century provided further data points. The solar storm of August 1972 struck between the Apollo 16 and Apollo 17 missions, a timing that, had it occurred during a lunar transit, would have delivered a radiation dose to the crew potentially exceeding the threshold for acute radiation syndrome. NASA's subsequent analysis of that storm became foundational to space radiation risk assessments for crewed spaceflight. The proton fluence, the total number of high-energy protons per unit area, recorded during that event was among the highest in the modern instrumental record. A crew in a spacecraft without the protection of Earth's magnetosphere, as Apollo astronauts were during lunar transit, would have had no effective shielding against that flux. The 1989 Quebec storm demonstrated that even a G5 event at solar maximum, significant but not Carrington scale, was sufficient to collapse a continental power grid in under 2 minutes. The post-event engineering analysis revealed a chain of failures that illustrated precisely how geomagnetically induced currents propagate through high-voltage infrastructure. The currents enter the grid through the grounding connections of high-voltage transformers. Unlike the alternating current that power grids are designed to handle, oscillating at 60 Hz in North America, geomagnetically induced currents are quasi-DC, meaning they are essentially direct current with very slow oscillation. Transformers are not designed to handle DC injection. When DC flows through an AC transformer's core, it drives the core into magnetic saturation. The steel laminations of the core become fully magnetized and can no longer respond linearly to the AC signal. The transformer begins drawing enormous reactive power from the grid, heating internally and generating harmonic distortions that propagate through the network and trigger protective relays at other substations. the failure cascades faster than human operators can respond. This is the vulnerability that keeps power engineers awake. Not the drama of aurora, not the spectacle of particles streaming from the sun, but the quiet, invisible flow of quasi-DC current through a grid architecture designed on the assumption that the ground is electrically inert. The ground is not inert. During geomagnetic storms, it becomes a conductor. The scientific turning point that changed humanity's understanding of this risk came not from a solar event, but from a network of magnetometers. In the 1990s and 2000s, researchers began correlating archived geomagnetic records with historical power grid disturbance logs and found a systematic relationship. Every significant geomagnetic storm correlated with measurable anomalies in grid behavior, transformer heating events, and relay activations, even at storm intensities well below G5. The threshold for infrastructure impact was lower than anyone had assumed. A G3 storm, moderate, occurring several times per solar cycle, was sufficient to produce measurable GIC flows in long transmission lines at high latitudes. A G4 event could stress transformers. A sustained G5 could destroy them permanently because the thermal damage to the transformer's internal insulation is irreversible. A large high-voltage transformer cannot be repaired in the field. It must be replaced. They are custom manufactured. They weigh between 100 and 800 metric tons. And as of the most recent industry surveys, the global spare transformer inventory for the highest voltage classes is measured in single digits, the insurance industry noticed. In 2013, Lloyd's of London published a detailed risk assessment of a Carrington-scale event striking the northeastern United States. The report estimated between 20 and 40 million people losing power, with outages lasting 16 days to 1 to 2 years depending on transformer damage. Total economic cost was estimated at between $600 billion and $2.6 trillion. The range is wide because the critical variable, how many transformers would fail, depends entirely on the storm's duration and the BZ orientation, the same variable that no instrument can forecast more than 45 minutes in advance. That same year, the Federal Energy Regulatory Commission in the United States issued Order 779, requiring the North American Electric Reliability Corporation to develop standards for the protection of the bulk power system from geomagnetic disturbances. The standards that eventually resulted, NERC TPL 007, require transmission planners to assess their system's vulnerability to a benchmark geomagnetic disturbance. Implementation has been gradual, uneven, and incomplete. As of the most recent compliance reports, a significant fraction of the highest-risk transmission assets in North America do not yet have GIC blocking devices installed on their transformer neutrals, the single most effective engineering mitigation for geomagnetically induced current damage. The Parker Solar Probe changed the scientific picture in a different way. Launched in August of 2018, it was designed to fly closer to the Sun than any previous spacecraft, eventually reaching a perihelion of approximately 6.1 million kilometers from the solar surface, well within the orbit of Mercury and deep inside the solar corona. At those distances, the probe is measuring the solar wind and coronal conditions in a regime that was previously entirely inaccessible. The data it has returned has already revised models of solar wind acceleration, identified previously unknown structures in the near-Sun environment, and provided direct measurements of the magnetic field topology in the inner heliosphere. One of its most significant early findings involved the detection of sudden, sharp reversals in the radial component of the heliospheric magnetic field. Brief intervals in which the field direction flips back toward the Sun before resuming its outward orientation. These structures, named switchbacks, were not predicted by pre-existing models of the solar wind. Their origin, their relationship to the coronal heating problem, and their role in solar wind acceleration are still active areas of research. What they demonstrate is that the solar wind is not the smooth, monotonic outflow that textbook diagrams suggest. It is structured, textured, and complex at scales that only in situ measurement can resolve. The Solar Orbiter mission, a joint ESA-NASA spacecraft launched in February of 2020, added a complementary capability, out-of-ecliptic observations that allow scientists to study the Sun's polar regions, which are poorly observed from the ecliptic plane where Earth and most spacecraft orbit. The Sun's poles are where the global magnetic field structure is rooted. the region that determines the overall polarity of the heliospheric magnetic field and the large-scale architecture of the solar wind. Solar orbiters' images and measurements of the solar poles at unprecedented resolution have revealed fine-scale magnetic structures and jets of plasma that feed into the solar wind in ways that are still being characterized. Together, Parker Solar Probe and Solar Orbiter represent the most capable observational infrastructure for solar physics ever assembled. And they are operating now, during the same solar cycle, Solar Cycle 25, in which the coronal hole responsible for the current event opened. Solar Cycle 25 began in December of 2019, at the minimum between Cycle 24 and the new cycle. Early predictions from the Solar Cycle 25 Prediction Panel, a group of international experts convened by NOAA and NASA, suggested it would be a below-average cycle, comparable in strength to the weak Cycle 24 that preceded it. Those predictions were wrong. Cycle 25 has proven significantly more active than anticipated, exceeding the predicted smoothed sunspot number by a substantial margin and producing multiple significant geomagnetic events. The solar maximum of Cycle 25, the period of peak activity, is now assessed to have occurred in or around 2024 to 2025, meaning the Sun is currently in a phase of elevated, though gradually declining, activity. That context matters. A coronal hole of the current size and position in a solar cycle more active than models predicted during a period of still elevated magnetic complexity on the solar disk is not a routine event. It sits at the upper end of the distribution of solar wind events that Earth experiences during normal solar maximum conditions. Whether it crosses the threshold into something more consequential depends, as it always does, on the interplanetary magnetic field orientation that no instrument will measure until the stream reaches L1. The 45-minute warning window has not changed since DSCO-VR was launched. The physics does not negotiate. The stream arrives without announcement. There is no visible flash, no audible signal, no detectable change in the light coming through a window. The solar wind does not announce itself to human senses. It is invisible, odorless, silent, a river of charged particles moving at 600 kilometers per second through the vacuum of interplanetary space, and then, without transition, through the outermost boundary of Earth's magnetic environment. The planet's instruments register it first. The magnetometers at high-latitude observatories, in Tromsø, in Yellowknife, and Resolute Bay, record a sudden northward deflection in the horizontal component of the local field. The bow shock has been pushed inward. The magnetopause has compressed. The solar wind dynamic pressure has spiked. The numbers change on screens in Boulder and Brussels and Tokyo, and the space weather forecasters begin the clock. This is the sudden commencement of a geomagnetic storm, the sharp, impulsive onset that has been recorded since the first magnetometers were installed in the 19th century, and that Carrington's contemporaries observed as a sudden deflection in compass needles across two continents simultaneously. The physics driving it is the same physics it has always been. The solar wind's dynamic pressure compresses the magnetosphere. The compression propagates as a magnetohydrodynamic wave through the magnetospheric plasma. That wave reaches the ground as a measurable perturbation in the geomagnetic field, a sudden impulse, lasting minutes, that precedes the main phase of the storm by hours. Then the BZ turns. The interplanetary magnetic field embedded in the solar wind stream, measured in real time by DSCO-VR at L1, rotates southward. The value crosses 0 nanotesla. It continues. -10, -20. The dayside magnetopause, the boundary between the solar wind and Earth's magnetic domain, becomes a site of intense magnetic reconnection. Field lines from the heliospheric magnetic field couple with field lines from Earth's magnetosphere. Open channels form. Solar wind plasma flows inward. The Dungy cycle accelerates. Energetic ions begin injecting into the inner magnetosphere, drifting westward, intensifying the ring current. The DST index, calculated in real time from the 4 equatorial magnetometer stations, begins its descent. At high latitudes, the effects are immediate and spectacular in the literal sense of the word. Something to be observed, something that produces light. The auroral oval, The ring-shaped zone encircling the geomagnetic poles where particle precipitation into the ionosphere normally produces aurora expands equatorward. Under quiet conditions, the auroral oval sits at roughly 65 to 70 degrees geomagnetic latitude, visible from Alaska, northern Canada, Scandinavia, and Siberia on clear nights. As the storm intensifies and the ring current grows, the oval expands. At G3 intensity, aurora becomes regularly visible at 50 degrees latitude, covering the northern continental United States, Central Europe, and comparable latitudes in the southern hemisphere. At G4 and G5, the oval can push to 40 degrees, 30 degrees lower. The physics that drives this equatorward expansion is well understood. The intensified ring current distorts the inner magnetosphere, pushing the boundary of the auroral zone toward the equator, expanding the region where field-aligned currents flowing between the magnetosphere and ionosphere deposit their energy as light. The light itself is a direct physical consequence of particle collisions in the upper atmosphere. Energetic electrons, accelerated along magnetic field lines and precipitating into the ionosphere at altitudes between 100 and 300 kilometers, collide with atmospheric molecules, primarily atomic oxygen and molecular nitrogen. Those collisions excite the electrons within the atoms and molecules to higher energy states. The excited electrons cannot remain in those states. They drop back to their ground states and release the excess energy as photons of light. The color of the aurora is determined by which atom or molecule is excited and from which altitude. Atomic oxygen at altitudes above 200 kilometers produces the characteristic red aurora. The crimson displays reported from tropical latitudes during the Carrington event. Atomic oxygen at lower altitudes between 100 and 200 kilometers produces the most common green aurora. The vivid emerald curtains and rays familiar from photographs taken at high latitudes. Molecular nitrogen produces blue and purple hues, most visible at the lower edges of auroral arcs where nitrogen density is higher. The aurora is not merely beautiful. It is a visible indicator of energy deposition. Every photon of auroral light represents energy transferred from the magnetospheric particle population, ultimately from the solar wind, into the atmosphere. During a major geomagnetic storm, the total power deposited into the ionosphere through auroral precipitation and associated ionospheric currents can reach 1,000 gigawatts or more. 1,000 gigawatts. The total electrical generating capacity of the entire United States, every power plant, every source combined, is approximately 1,100 gigawatts. The storm dumps energy into the atmosphere at a rate comparable to the entire American power grid running at full output. That energy does not come from any human source. It comes from the sun, transported across 150 million kilometers of space by the solar wind, converted through the magnetospheric system, and deposited directly into the top of the atmosphere in a matter of hours. That energy deposition drives the ionospheric current systems, the auroral electrojet in the high-latitude ionosphere, and the equatorial electrojet along the magnetic equator, to intensities far above their quiet time values. These currents flow horizontally through the ionosphere at altitudes of roughly 100 to 130 kilometers. They are enormous in scale, spanning thousands of kilometers in length and hundreds of kilometers in width. And their rapid variations in intensity and direction, driven by the changing conditions in the magnetosphere above, produce rapid variations in the magnetic field at Earth's surface below. Those rapid variations are what drive the geomagnetically induced currents, the GICs, that flow through power grids, pipelines, and telecommunications cables. The rate of change of the magnetic field, measured in nanotesla per minute, is the variable that engineers care most about, because GIC magnitude scales with how rapidly the surface field is changing, not simply with how disturbed the field is in absolute terms. During the most intense phase of a major storm, rates of change exceeding several hundred nanotesla per minute have been recorded. The GICs induced by such rates in long transmission lines at high latitudes can reach hundreds of amperes. A transformer designed to handle normal operating conditions encounters a DC injection of that magnitude and begins saturating. Its reactive power demand spikes. The grid frequency destabilizes. Protective relays trip. Sections of the network separate. The cascade begins. Meanwhile, at altitudes between roughly 1,000 and 60,000 kilometers in the radiation belts, the Van Allen belts, something different is happening. The Van Allen belts are two concentric toroidal regions of trapped energetic particles encircling Earth, discovered in 1958 by instruments on Explorer 1, the first successful American satellite, and named for the physicist James Van Allen who designed the experiment. The inner belt, centered at roughly 1.5 Earth radii, is populated primarily by energetic protons produced by cosmic ray interactions with the atmosphere. The outer belt, centered at roughly 4 to 5 Earth radii, is dominated by highly energetic electrons, relativistic electrons with energies reaching millions of electron volts, whose population varies enormously with solar and geomagnetic activity. During the main phase of a geomagnetic storm, the outer radiation belt undergoes dramatic and complex changes. The initial compression of the magnetosphere can enhance the electron population. The injection of fresh plasma from the magnetotail during substorms, explosive releases of energy stored in the magnetotail that occur episodically throughout the storm's main phase, seeds the outer belt with new electrons. Over hours to days following the storm, wave-particle interactions in the magnetosphere can accelerate those electrons to relativistic energies through a process involving chorus waves, electromagnetic plasma waves generated at the magnetic equator and propagating along field lines. The resulting population of ultra-relativistic electrons, sometimes called killer electrons, poses a direct threat to satellite electronics. Relativistic electrons can penetrate satellite shielding and deposit charge inside the spacecraft's electronics, causing deep dielectric charging, a slow accumulation of charge in insulating materials that eventually discharges in a sudden electrostatic spark. That discharge can permanently damage or destroy solid-state electronics. Satellite operators respond to storm warnings by switching sensitive instruments to safe mode, reorienting spacecraft to reduce exposed surface area, and postponing maneuvers that require precise attitude control, because the magnetosphere's changed configuration makes star tracker and magnetometer readings less reliable. Mission operations centers at NASA's Goddard Space Flight Center, at the European Space Operations Center in Darmstadt, at SpaceX in Hawthorne, and at dozens of other facilities around the world track the storm's progression in real time and implement contingency procedures calibrated to the storm's current intensity. At the surface, at high latitudes, the substorms driving much of this activity produce their own geomagnetic signatures. A substorm, a discrete, explosive release of energy from the magnetotail, produces a sudden intensification of the auroral oval, a rapid brightening that can occur within minutes, and a sharp deflection of the surface magnetic field at high-latitude stations that can reach several thousand nanotesla in amplitude in a matter of minutes. Substorms are not the same as the storm itself. They are episodic events embedded within the larger storm context, each one representing a separate loading-unloading cycle of the magnetotail. During a prolonged storm driven by sustained southward BZ, substorms can occur every 1 to 3 hours, each one injecting fresh plasma into the ring current and adding to the storm's total intensity. The DST index continues its descent through the main phase, -50, -100. The ring current is now carrying a substantial westward electrical current around Earth, its magnetic effect measurable on every magnetometer on the planet's surface. At the poles, the aurora blazes. At mid-latitudes, compass needles deviate from their normal bearings by measurable fractions of a degree. At the equator, the effect is smaller, but still detectable. The planet's magnetic field, 4.5 billion years old, is responding, flexing, distorting, absorbing. Then, at some point determined entirely by the solar wind's own evolution, by when the southward BZ finally rotates northward again as the trailing edge of the coronal hole stream passes, the injection of energy into the ring current slows. The ring current begins to decay, its energetic ions lost to charge exchange with the neutral hydrogen geocorona, the faint outermost envelope of Earth's atmosphere extending tens of thousands of kilometers into space. The DST begins its slow recovery, rising back towards zero over the course of 12 to 48 hours. The auroral oval retreats poleward. The ionosphere cools and contracts. The GIC flows in power lines diminish. The storm ends the same way it began, quietly, invisibly, without announcement. The solar wind stream moves on, traveling outward past Earth, past Mars, past the asteroid belt, eventually joining the broader heliospheric flow that fills the solar system to its outermost boundary. Earth's magnetic field closes behind it. The magnetopause returns to its normal position. The bow shock settles. The instruments in Boulder record the recovery phase and begin calculating storm statistics: peak DST, maximum KP index, total energy input, GIC event logs from grid operators. The data joins the archive. Another event in a continuous record stretching back to the first magnetometer readings of the 19th century, each one a data point in humanity's slowly deepening understanding of its relationship with the star 93 million miles away. The sun did not notice. It continues burning, fusing, releasing. The coronal hole that produced this event remains open, rotating with the solar disk, aimed now at different regions of interplanetary space. In approximately 27 days, Earth's orbital position will bring it back into alignment with the hole. The solar wind stream will form again. The process will repeat. It has been repeating for 4.5 billion years. The storm is over. The data says so. The DST index has climbed back from its minimum, recovering along the characteristic exponential curve that ring current decay always follows, steep at first, then gradual, flattening toward zero over the course of a day and a half. The KP index, the Planetary Geomagnetic Activity Index, calculated every 3 hours from a network of 13 subauroral magnetometer stations distributed around the globe, has dropped from its storm time peak back toward quiet time values. The auroral oval has retreated to its normal position near the poles. The ionosphere has cooled. The thermosphere has begun contracting back toward its quiet time altitude profile. The GIC monitors at high-latitude power substations show currents returning to background levels. The instruments, one by one, return to their baseline readings. The sun, from Earth's surface, looks exactly as it did before the storm. The same disk, the same light, the same warmth on skin. Nothing in ordinary human experience marks the passage of the event. No crater, no residue, no visible scar on the landscape. The storm moved through the planet's magnetic environment as completely and as silently as it arrived. That invisibility is itself a profound physical fact. Earth's magnetic field absorbed the energy of a fast solar wind stream, a stream carrying dynamic pressure several times above the ambient baseline, embedded with a sustained southward interplanetary magnetic field, and dissipated that energy into the ionosphere, the thermosphere, and the radiation belts over the course of roughly 18 hours. The total energy input to the magnetospheric system during a moderate to strong geomagnetic storm, integrated over the entire storm duration, is measured in units of petajoules. 1 petajoule equals 1 quadrillion joules. A major storm can deposit between 1 and 10 petajoules into the magnetosphere-ionosphere system. The nuclear weapon detonated over Hiroshima in August of 1945 released approximately 63 terajoules of energy. 1 petajoule equals roughly 15.9 Hiroshima-scale events. The magnetosphere absorbed the solar wind's energy contribution, equivalent to dozens of such events, silently, continuously, invisibly, and the surface of the planet registered it only as compass needle deflections, radio propagation anomalies, and, at high latitudes, light. That is what the magnetic field does. That is what it has always done. The question of how long it will continue to do so is not rhetorical. It is a live scientific question with a concrete, measurable answer that changes slowly over geological time. Earth's magnetic field has been weakening. The global average surface field intensity has decreased by approximately 9% over the last 170 years, the full duration of the modern instrumental record. The South Atlantic anomaly has grown in area and deepened in intensity over the same period. Paleomagnetic data, the record of ancient field directions and intensities preserved in volcanic rocks and ocean sediment cores, shows that the current weakening is consistent with the early stages of a geomagnetic excursion or reversal. The last full reversal, the Brunias-Matuyama event 780,000 years ago, took somewhere between 1,000 and 10,000 years to complete. During a reversal, the field does not simply flip instantaneously. It weakens, becomes multipolar and chaotic, with multiple magnetic poles appearing at various latitudes simultaneously before eventually reorganizing into a new stable dipole configuration with reversed polarity. During that transitional period, the field's ability to deflect the solar wind is reduced. The magnetopause moves closer to Earth. The auroral zones expand dramatically toward the equator, not as a temporary storm effect, but as a sustained condition. The atmospheric stripping that the solar wind constantly attempts, the same process that stripped Mars's atmosphere after its dynamo failed, accelerates. The radiation environment at the surface worsens. Satellite electronics are more exposed. The geological record does not show evidence of mass extinctions coinciding with previous geomagnetic reversals, which suggests that the atmosphere retains sufficient shielding thickness even during a weakened field period to protect surface life. But the technological civilization that now inhabits this planet did not exist during the last reversal and has no empirical experience of operating in a significantly weaker geomagnetic environment. These are not distant, abstract concerns. The rate of magnetic North Pole drift, 55 kilometers per year as of the most recent measurements, a rate that has accelerated significantly compared to historical averages, has already forced updates to the world magnetic model, the mathematical representation of Earth's magnetic field used by GPS systems, aircraft navigation software, and smartphone compass applications. The model, maintained jointly by NOAA and the British Geological Survey, is updated every 5 years. In January of 2019, an unscheduled out-of-cycle update was issued because the pole's drift had moved it outside the acceptable error bounds of the existing model ahead of schedule. The field is changing fast enough that the navigation infrastructure built on top of it requires monitoring and correction on timescales shorter than originally planned. The Sun's own cycle adds another layer of temporal structure to this relationship. The approximately 11-year sunspot cycle, more precisely, the 22-year Hale cycle that tracks the full reversal and return of the solar magnetic polarity, modulates the frequency and intensity of geomagnetic events. At solar maximum, active regions are more numerous, flares are more frequent, coronal mass ejections occur more often, and the solar wind is more structured and variable. At solar minimum, the sun's output becomes more uniform. Coronal holes tend to persist at polar regions, and the slower, less magnetically complex solar wind produces fewer geomagnetic storms. The current solar maximum of cycle 25, which exceeded the pre-cycle predictions of the International Forecasting Panel, has produced a period of elevated activity that the historical record places in the moderately high range. It is not the most active solar maximum on record. Solar cycle 19, peaking in 1958, holds that distinction in the modern era, with a smoothed sunspot number of nearly 200. But it is significantly more active than the weak cycles 23 and 24 that preceded it, and it has reminded operational space weather forecasters, satellite operators, and power grid engineers that the sun's variability does not follow linear trends. Each cycle is its own event. Each solar maximum brings its own distribution of flares, CMEs, and coronal hole streams, and the most extreme events within each cycle are determined by specific magnetic configurations that cannot be predicted from the cycle's average activity level alone. The coronal hole responsible for the event just passed will rotate out of Earth-facing alignment over the next several weeks. But the cycle continues. Other active regions will develop. Other coronal holes will open. The processes generating them, differential rotation, convective turbulence, magnetic flux emergence from the solar interior, are continuous. They have been continuous since the Sun entered its main sequence phase approximately 4.5 billion years ago, and they will continue for another 5 billion years until the Sun exhausts its core hydrogen supply and begins its terminal evolution into a red giant and, eventually, a white dwarf. On that final timescale, the relationship between Earth and Sun will end in a way that makes every geomagnetic storm in the current era look like a trivial fluctuation. As the Sun expands into its red giant phase, its luminosity will increase by a factor of several thousand. Its radius will grow to encompass the current orbits of Mercury, Venus, and possibly Earth itself, depending on mass loss rates and orbital migration. The solar wind during this phase will be far more intense than anything the current main sequence Sun produces. The magnetosphere will be overwhelmed. The atmosphere will be stripped. The oceans will boil. The surface will be sterilized. The geological record that currently preserves the paleomagnetic history of Earth's relationship with the solar wind, the magnetized minerals in volcanic rocks, the sediment cores, the ice cores, will be vaporized. That is the terminal condition. That is where the physics leads, given enough time. Between now and then, the relationship continues. The solar wind presses outward in all directions. Earth's magnetic field holds. The magnetopause sits at roughly 10 Earth radii, negotiating the boundary between the sun's domain and the planet's. The ring current drifts westward, slowly dissipating. The ionosphere radiates its last auroral photons of the current storm. The bow shock settles into its quiet time position. The 45-minute warning window at L1 stands watch, the DSCOVR spacecraft measuring the solar wind's properties in the cold silence of the first Lagrange point, transmitting its data stream toward a planet that depends on those measurements more than most of its inhabitants will ever know. Richard Carrington sketched his observations on that September morning in 1859, ran to find a witness, returned to find the light already gone. He noted the event in his logbook with characteristic scientific restraint, recording the time, the position, the duration, the brightness. He did not fully understand what he had seen. The physics connecting the white light flash above a sunspot to the geomagnetic storm that began 17 hours later was not established until decades after his death. The full chain of cause and effect, from coronal magnetic field structure to solar flare, to coronal mass ejection, to interplanetary transit, to bow shock, to magnetopause reconnection, to ring current injection, to auroral precipitation, to geomagnetically induced current, took more than a century of spacecraft observations, ground-based measurements, theoretical development, and computational modeling to trace end to end. That chain is now known. Not completely. The coronal heating problem remains unsolved. Switchbacks remain incompletely explained. The precise trigger conditions for major CME eruptions cannot yet be predicted more than hours in advance. The frontier of solar and heliospheric physics is still active, still producing surprises, still requiring new instruments and new theoretical frameworks to advance. But the fundamental fact that Carrington's observation pointed toward, without his being able to name it, that Earth and Sun are physically coupled systems, that the boundary of our planet is not the atmosphere, but the magnetopause, that the space between the Sun and Earth is not empty but filled with a structured, dynamic, magnetically organized medium that connects the two bodies in real time. That fact is now established beyond any reasonable scientific doubt. The hole in the Sun opened. The stream crossed 150 million kilometers. The magnetosphere responded. The aurora burned at latitudes that rarely see it. The instruments recorded every step. The storm passed. The sun continues to burn. The field continues to hold. And somewhere above the polar ice, the last auroral curtain of this particular storm fades from green to black. Not because the sun is finished with Earth, but because this particular conversation between the star and the planet has, for now, reached its end.